Hello and welcome to section 6.4, where we're going to talk about equilibria in reactions and how that relates to the Gibbs free energy. So with that in mind, let's look at a reaction. Let's look at a reaction here where we're going to have some mixture of reactants in equilibrium with some mixture of products. Okay, and in this reaction, we expect there to be some energy associated with both the reactants here, and we expect this reaction to be somewhat spontaneous, which means when you put in the reaction profile, there's also a negative delta G, which tells us that the reaction should be spontaneous. So we let this reaction go to its equilibrium, and we find out that there's actually still a mixture of products and reactants present in our flask. And we ask, why is that? Because the reaction is spontaneous. Doesn't it go all the way from A plus B to C plus D? And the answer is it depends. It depends on if the system is at equilibrium. It depends on what the magnitude of the negative delta G value is. And it turns out that we can actually solve for the negative delta G simply from knowing our proportion of products and reactants. So to do that, we're going to use a friend that we learned in general chemistry, and that is the KEQ equation. And if you remember, KEQ is equal to the concentration of products times the concentration, over the concentration of the reactants. So if we know our concentrations of each, then we can use this equation that relates delta G to our equilibrium constants, which is delta G is equal to negative RT natural log of KEQ. And I guess I should make this KEQ a little easier to see, because this is actually the natural log of KEQ. There. Okay. So if we know a KEQ value, it's really easy just to plug in numbers to get the delta G values that we're interested in, or to find the delta G value of a reaction. And in this equation, R is equal to 8.314 joules per mole Kelvin. KEQ is a dimensionless value, and T is equal to temperature in Kelvin. So if we imagine that our reaction, our KEQ, let's see, so if KEQ is equal to, well, let's say 10, so the reaction goes towards products but not super strongly, then we can solve this if T is also equal to 298. And if that's the case, then we have delta G is equal to negative 8.314 times 298 times the natural log of 10, which is equal to negative 8.314 times 298 times 2.3, which is equal to negative 5,698.4156 joules per mole, which is equal to negative 5.7 kilojoules per mole. So that's one way, as you can see, that we can go from a KEQ value, that is the concentration or the equilibrium concentrations of reactions and products, and find the delta G for a reaction. So this covers really with enthalpy, entropy, and Gibbs free energy. This covers what we're going to call thermodynamics, which leads us to a question looking back at this reaction energy diagram. We talked about if something is spontaneous, but what we haven't talked about is how fast do reactions occur. That's a whole other can of worms that hopefully we will cover in the coming chapters. And this has been section 6.4.